Great. So welcome everybody to this course on shared memory programming with OpenMP. I'm just going to start by going through a few bits of preliminaries and logistics. Okay, so just to be clear about the legal stuff, okay, so essentially this material is all free for you to copy and redistribute and use as you see fit under the terms of the license. Okay, yes, okay, let's get on to, so just to introduce a little bit about the ARCHER2 service, so which is providing this training course. So ARCHER2 is the UK's national supercomputing service. It's managed by UKRI, well, primarily EPSRC. It's housed and supported and operated by us at EPCC, and this hardware is supplied by Cray, otherwise known as HPE Cray. Okay, and this training is provided by members of the ARCHER2 computational science and engineering team at EPCC. So we provide quite a bit of training throughout the year, both in person and online like this. Okay, so it's a little bit about the hardware. So ARCHER2 system has a little under 6,000 nodes. Each of those has 128 cores per node, so something approaching 750,000 cores in total. There's 256 gig per node on most of the nodes. A few of them have a bit more. It uses the Cray Slingshot interconnect and various high-performance file systems. So of course, with OpenMP, we're really just interested in programming on a single node. So that's all we'll be looking at in this course. Okay, I think I'll skip over some of this stuff. Yeah, okay, ARCHER2 resources. So the link for the material for this course is available if you go to the ARCHER2 website under the training tab, or that's the link at the top there. You'll find this course instance. So that has the timetable. It has all the course materials. So lecture notes, practical exercise sheet, and the template code for the practical exercises. It also has a course chat page, which we will use for if during the course outside of the lecture times, if you want to ask questions about the practical exercises, or you have any issues with access to the machine and so on, then we'll use that, and I'll say a little bit more about that later. Okay. So at some point after this course, the material will be migrated into the past courses materials page. So it will continue to exist on the ARCHER2 website, sort of semi-indefinitely. There's other material there as well. There's various virtual tutorials, and also when you're using the machine, you might want to refer to the user documentation as well. Okay, introduce myself. My name is Mark Bull. I'm a senior research fellow at EPCC. I teach this material and other things to our master's students, and I'm also EPCC's representative on the OpenMP Architecture Review Board, which is the formal body which maintains and enhances the OpenMP standard. Okay, other things. Yep, I will remind you towards the end of the course, ask you for feedback. If you've got any general questions about ARCHER2, I should say ARCHER2 there, or if you need support with your accounts that I can't solve immediately, then please contact the help desk. Okay, so you can get access to ARCHER2. If you don't already have an ARCHER2 account, then you can apply for one. You'll have received the instructions, I hope, as to how to do that. So you'll get an account under project TA164 for the duration of this course and a bit longer. We won't actually have reservation access for this course because we're operating over multiple days, so we won't do that. But if you use if you have your own ARCHER2 account, then you're perfectly free to use that. You can all the exercises run in less than a minute, or should run in less than a minute. So you can use the short queue for quick job turnaround. So the accounts will be closed around about 2 weeks after the end of the course, and everything will get deleted. So just make sure that if you want to take copies of anything that you've done in those temporary accounts, then please copy them off before the accounts get blown away. Yeah, as I said before, all the material is available on the ARCHER2 website, and it will be archived there semi-indefinitely. Okay, there is a code of conduct which we invite you to abide by. So in particular, ask you to use welcoming and inclusive language, be respectful of other people, and so generally be nice and pleasant and sensible. Okay, I will skip that stuff as well and move on to the timetable for this course. So we're trying something a little bit new, as you'll have noticed, for this course by running it over a series of morning sessions. So the idea here is really to allow you to have to be able to work on the practical exercises in your own time. There will be some time built into these towards the end of the morning sessions for you to do that, and I'll be around to support you, but also to give you enough time in between the sessions to work on the practical exercises yourself. And also we will aim to get the recordings of these sessions up and available as soon as we can, so that if you're unable to attend one of the sessions, you should be able to catch up via the recordings. So today we'll be looking at shared memory concepts in general and an introduction to OpenMP, without really going into any details of syntax. So that'll come tomorrow when we look at parallel regions and work sharing. Then on Thursday we will look at synchronization and some other topics. And then the final lecture session will be next Tuesday, which will cover some things about practical hints, tips, tricks, and gotchas, and we'll also be talking about performance issues in that session. And then finally, a week on Thursday, there'll be a session where I will talk through the solutions or possible solutions to the practical exercises. as I say, you're encouraged to work on the practical exercises when it's convenient for you. There should be a little bit of time for you to do that at the end of each of the first 4 morning sessions, I'll be around online to help out. But outside those times, please use the course chat link on the web page to ask questions. I'll be keeping an eye on that on a regular basis and doing my best to answer any of your questions. Okay, I think okay. We'll come back to this when it's time. But the practical exercises, the source code, so it's available via the course materials page, but for convenience, there's also a copy just in a shared directory on ARCHER2, so you can just copy it directly into your own directory and unpack it. And I'll show this slide again when it's time to do that. Okay. Hope you're going to enjoy the course. As I say, it's always a little bit difficult online, but I really do encourage you to ask questions. So probably the most convenient way to do that is via the chat facility on the Collaborate page. So you can find that by opening the Collaborate parallel, which you do with the little purple arrows, which should be at the bottom right hand side, and then if you click on the little speech bubble, that will give you access to the chat for these sessions, and you can please type your questions in there. If you prefer to speak, then that's absolutely fine. Please use the raise your hand facility at the bottom. And I'll keep an eye on and try to respond to all your questions. Okay, does anybody have any questions before we start? Okay, so I should have said we'll also be. I'll schedule in a break during these morning sessions. I'm not so depending on the length of the lectures. I'm not sure exactly what time it'll be, but somewhere in the middle of the morning we'll take a half-hour break. Good, so I'm going to begin by talking about some concepts in shared memory programming, which underlie how OpenMP works, but also apply to other shared memory APIs as well. So I'm going to start off by talking a very little bit about hardware, just enough so that we have a mental picture of the systems that we're working with and how they operate, and then I'll cover some basic concepts in threaded programming. So this is, as I said, it's not OpenMP specific. It really applies to any programming model that relies on threads and shared variables. Okay, so shared memory systems. So threaded programming, this concept of using threads and shared variables is most often used on shared memory parallel computers. What's one of those? Shared memory computers essentially consists of a number of processing units, so CPUs or cores, together with some memory. But the key feature of these shared memory systems is that there is a single address space across the whole memory system. So what does that mean? It means that every CPU or core is able to read and write all the memory locations in the system. So the entire memory appears as one logical memory space, and all the cores refer to a memory location using the same address. So conceptually, what we have is a picture like this. So we have a number of independent processing units, cores here along the top, and we have one memory space to which all these cores are connected. And every core is able to access and read and write all the memory locations. So that's kind of our conceptual model as a programmer. Of course, real hardware is way more complicated than this. So for several reasons. So in particular, the memory may actually be split up into multiple smaller units. And then there also may be multiple levels of cache memory. And some of those levels may be shared between some subsets of processors. And the interconnect might have some more complicated topology. But nevertheless, if it's a shared memory system, then we're still talking about something where a single address space is still supported. And all this hardware complexity is certainly able to affect the performance of programs, but not their correctness. So the complexity of the design of the hardware is such that it still presents to us as a programmer this simple model of the hardware that we saw before in terms of correctness and how programs behave in terms of the results that you get. But this complexity can of course affect performance. Okay, so just to illustrate that, so for example, here's a slightly more complicated system. Okay, so here now instead of one single flat memory, we've actually got memory split into two pieces, and each of those has some processors associated with it, and those processors, so I've just shown two here. Each of these processors has its own level 1 cache, and they share a level 2 cache. And then there's some interconnect here which allows processors not only to access their own memory, but also to access the memory belonging to other groups of cores. So this can be this is typically different chips in a system. So we often build nodes of large supercomputers using more than one chip. At the moment, the magic number for almost all system designs is 2. Okay, so almost all machines you're likely to come across at the moment, including ARCHER2, have 2 sockets in each node, and so each of those. So in ARCHER2 there are a node consists of 2 sockets. Each has an AMD ROM chip in it with 64 cores. So that's how we get the 128 cores per node. So in the past and possibly in the future again, we might see, and very occasionally you do come across them. You might see systems with maybe 4 4 sockets in a node. But for the with the current hardware technology, 2 seems to be the optimum number. So of course we can have. Madi asks, is a dual socket machine the same as a system with a dual CPU motherboard? Yes, essentially. Yeah. Yep, that's right. So of course, this is still a simple diagram in the sense that chips are much bigger, have order of 64, 72 cores on chips these days. Common design is to have 3 levels of cache, so level 1 and level 2 per core typically, and then level 3 shared between some subset of cores, not necessarily all the cores on the chip. But nevertheless, despite all this complexity, it's possible for, say, this core here to access memory both in this part of memory and in this part of memory completely transparently to the program. Okay, so when we write and run our programs, it's entirely up to the system where it actually stores the data. We can have some control over that. We'll talk a little bit about that when we come to performance issues. But essentially, it's all transparent, and all the storing of copies of data in caches again that's all done in the hardware and is completely transparent to the program. It's kind of transparent that even at the hardware level, really, because the all the core is doing is issuing loads and stores for virtual addresses, and then the hardware takes care of where those virtual addresses are physically mapped into main memory, and how those addresses are then get temporary copies stored in the caches as the application executes. The CPU itself doesn't really know anything about that. So there's kind of this decoupling at the hardware level as well as at the program level. Okay, that's really all I'm going to say about hardware for the time being. So we'll return a little bit to it in the performance session at the end of the course. But does anybody have any other questions at the moment about the hardware? Okay, so let's sort of move up a little bit to the software level and talk about the threaded programming model. So the programming model for shared memories is based on this notion of threads. So essentially, threads are like processes. They're an instance of a running program, except that threads can share memory with each other, as well as having their own private memory. Okay, so by default, if we run separate processes on the same system, then by default they have separate memory spaces. So it's possible to organize for processes to share memory with each other, but you have to do something special to enable it. So by default, processes have their own separate memory spaces. But by default, multiple threads so again, this is usually done in most operating systems, have multiple threads running inside a single process or single operating system process. And by default, those threads have access to some shared memory. So that means in this programming model, we end up with two types of data. There is shared data, which can be accessed by all the threads. And then there is private data, which can only be accessed by the owning thread. And this is entirely a software level construct. There is absolutely no distinction between how the hardware handles these different types of data. The hardware knows nothing about this. So the hardware will treat all the data exactly the same. This distinction between shared and private is purely a software level concept. So in order to do useful parallel programming, what can happen, or what happens, is that different threads follow different flows of control through the same program. So we're really thinking about running a single executable, but this will create multiple threads which will do different things, will take different paths through the same program. So another way of thinking about that, or so taking that down to the hardware level, is that each thread has its own program counter. So each thread has its own notion about which machine instruction it's going to execute next. Usually for performance reasons, we tend to think about having a one-to-one mapping between threads and cores. So normally we will run exactly one thread per core in the system. You don't have to do that. It can be more. So the operating system is perfectly happy for you to run lots more threads than you have cores, and it will try to give a fair share of the hardware resources to all the threads that you're running. In a high-performance computing situation, that's generally a bad thing, because that sharing of hardware resources implies having to stop one thread running and start another thread running. So that's context switching. And that's an expensive process, which we want to avoid if we want good performance. A lot of modern hardware does, in fact, have hardware support for multiple threads per core. And again, the usual magic number here is 2. Okay? So most modern chips will allow you to have some hardware support that allows you to reasonably efficiently execute 2 threads per core without the operating system having to get involved to do context switching. Again, we'll talk about this in the performance. Talk about more about this when we come to performance issues. But for most applications, that doesn't actually really help. Okay? And so we tend to run only 1 thread per core for performance reasons. And you'll find that most supercomputers, including ARCHER2, are configured to run 1 thread by default, 1 thread per core by default. And usually, if you want to use the extra thread per core, extra hardware thread, then you have to do something special to request that. Okay, so just to put this into a picture, so this idea that we have multiple threads executing. So I've shown 3 threads here. Each thread has its own program counter. So that's so each thread will operate an independent stream of instructions. Each thread has some private data which only it has access to, but then all the threads have access to some shared data in the program. Okay, so this brings us on to the notion of how threads communicate with each other. So in order to have useful parallel programs, which are do something other than completely trivial parallelism, then threads have to be able to exchange data with each other somehow. And the way this works is very simple, really, conceptually. Is threads communicate with each other via reading and writing the shared data. Okay, so if I want to communicate some value of a piece of data from thread 1 to thread 2, then thread 1 can write the value to some shared variable, let's call it A, and then at some point later, thread 2 is able to read the value from A, and that's accomplished in an exchange of a value between the 2 threads. So this is just to emphasize that, in contrast to message passing, so to APIs like MPI, there is no notion of messages in this programming model. So threads don't send messages to each other. They are able to exchange data by reading and writing shared memory. Okay, so let's just walk through a little scenario to show how this happens. So here I have 2 threads. I'm going to show little bits of program that they're going to execute. And here we have the private data for each thread. And the little box is basically one variable inside that private data. And then we have the shared data at the bottom. And again, there's one variable highlighted inside that shared data area. So in order to do inter-thread communication, so what we might do is that, first of all, the thread 1 writes a value 23 into a variable called myA, which happens to live in the private data space for thread 1. So thread 1 can then, for example, copy that value into a variable called A, and A happens to live in the shared data space. And then sometime later, thread 2 can read the value of A from the shared data space, and then maybe do something with it. Okay, so in this case, thread 2 is going to add 1 to it and store it in its copy of myA, which lives in its own private data space. Okay. So this really just lets us see how thread communication happens, and also makes this distinction between shared and private data. Okay. So myA is a private variable. Each thread has its own copy of myA, and those copies can contain different values. On the other hand, A is a shared variable, so it lives in the shared data space. There only is one copy of that, and it has a unique value at any given time. Well, that's a slight simplification, but let's not worry too much about that just now. Okay, there is a slight subtlety here, is that shared data doesn't really have a unique value at every point in time. It has a unique value at certain specific times during the program, and in between we don't really know. But that's the kind of detail which is which we don't really ever have to care about very much. So I will talk a little bit about that again later on in the course. Okay, any questions so far? So Anthony asks, can the shared data be modified by two threads? And the answer is yes, but we have to be very careful about that. Okay, and that's what I'm going to cover next. Okay, so that brings us on nicely to the next topic, which is synchronization. So by default, our threads execute asynchronously. So that means that each thread proceeds through program instructions independently of other threads. So a thread doesn't, just keeps on executing by default without knowing what any of the other threads in the program are doing. So this means that we need to ensure that actions on shared variables occur in the correct order. Okay, so in that previous example, we have to make sure somehow that thread 1 writes variable A before thread 2 reads it. And sometimes we want the other way around. Okay, sometimes we want, we want the opposite effect. We want thread 1 to read the old value of A before thread 2 writes something new into it. And the other important thing to realize is that if we do an update to a shared variable, so if we have a program statement that looks like, A equals A plus 1 or A plus plus in C, then an action like that, although it's a single program statement, that's not an indivisible atomic action. So why not? Well, although it's a single program statement, it needs to be translated. When it gets translated down into machine code, into assembly code, that will require at least 3 instructions. There will be a load of A from memory into a register. There'll be the actual addition, which will produce a result, typically produce a result in, well, maybe the same register, maybe another register. And then the value has to be stored back from the register into main memory. So there'll be a load instruction, an add instruction, and a store instruction, at least, okay, to accomplish something like that. And if 2 threads try to do that at the same time, then the instructions can be interleaved in time such that one of those updates can get overwritten. And I'll illustrate for you now exactly how that kind of thing can happen. Okay, so what does Anthony asks, what does atomic action means? It means a single indivisible action which, from the perspective of other cores or other threads, happens all at once and there isn't a there aren't intermediate states during it that can be observed. Okay, and so it appears to complete in a single. Well, how to say this? It appears to complete. It's either hasn't happened or it has happened, and there aren't any intermediate states that can be observed during it happening. Okay, so hopefully this example will make it a little bit clearer what's going on here. Okay, so now I'm really talking about really looking at the hardware level. Okay, so we have 2 cores here, and I'm going to show you the some sort of pseudo assembly codes which they're executing, and the CPU registers where they're going to store value in them. Okay. And so I think that these is connected to memory. Okay, so we're for this purposes, we can completely ignore any complexities of the memory system. They you know, to do with caching or whatever. That doesn't matter here. Okay, so again, from the point of view of the cores, this is a real hardware thing. Okay, you know, the cores are really just don't know what's out there in terms of memory. Okay. The cores just issue load and store instructions for addresses that do their thing, and the memory system takes care of all the complexity external to the cores. Okay, so start off with a value in our variable a. So again, suppose it contains the value 10 to begin with. Okay. And I've got a thread running on each of these cores, and both of those threads want to add 1 to A. Okay, they both want to execute A equals A plus 1 or A plus plus. So if we don't do any synchronization, something like this could happen. Okay, so first thing that happens is that core 1 does the load of A. So it gets the value 10 in its register. Then core 2 does the load of A, so it gets the value 10 in its register. And core 1 does the addition. So, and the result of the addition is stored in the register. So we got value 11 here. And then core 2 does the same. And then core 1 stores its value back into memory. So the value in memory is now 11. And so you can probably see what's going to go wrong here. Final thing happens is that core 2 stores its value also back into memory, and end up with a value in memory of 11. Whereas we started with 10, 2 threads added 1 to it. So we would have really liked to get the value 12, but because these instructions got interleaved in a certain way, we can end up with the value 11. If we'd somehow arranged for core 1 to do all its instructions first, so in particular, as long as core 1 does its store before core 2 does its load, then we would have got the value 12, which we wanted. So what does this mean? Okay, at the programming level. So this problem is an example of what's called a race condition. And a race condition is, so the definition is when multiple threads access the same memory location without any synchronization, and at least one of those accesses is a write access. And so what that means is that if we don't do any synchronization, the threads are executing asynchronously, so we don't know, we can't guarantee any orderings of those accesses. So different time orderings of those accesses might happen, and that can result in non-deterministic behavior. Okay, so this is a very unpleasant situation. It means that running the same program with the same inputs twice may give us different results. And this is a really very nasty type of bug because it's non-deterministic. It means it's not reliably detectable by conventional software testing procedures. Okay? So you can't just write test suite, your conventional test type of test suite or test programs to catch this sort of bug, because sometimes it might happen, sometimes it might not. You might be in a situation where you can run the program 100 times, and the first 99 times you get the right answer, and then the 100th time you get the wrong one. So this is essentially, in essence, this problem is the thing that makes parallel programming with shared memory difficult. Okay, so it essentially all comes down to this idea that unsynchronized accesses to memory can result in non-deterministic behavior. So we have to be sure and very careful to make sure that all our threads are always correctly synchronized with respect to the memory accesses that they're making. Yeah, so that's where the difficulty comes from. You might ask yourself, well, why can't you just design this out in the hardware? And the answer is, well, you could, but it would be so inefficient that it wouldn't be worth it. Okay, so you could conceivably design your hardware in such a way that you could that essentially would force every memory access to be or every memory update to be atomic. Okay, you could do that. But the resulting performance would be so terrible that it wouldn't be worth it. Okay? So you'd have guaranteed safe programs, but the whole point of having or most of them, as far as at least our community is concerned, is the whole point of having parallel programs is to make them go faster. So so you would just defeat your primary purpose by doing that. Okay. Yeah. So in the next session, then we'll talk about these sort of mechanisms we have available in OpenMP to synchronize threads, but that's to come later. Okay, so the next concept I'm going to talk about is tasks. A task is really just a piece of computation which can be executed independently of other tasks. So if you like, when we're writing parallel programs, the fundamental thing that we're trying to do is to identify tasks, to identify pieces of computation that can be done independently and therefore can be executed by different threads at the same time. And that's how we're going to gain performance. In principle, what we could do is create a new thread to execute every task. Okay, so every independent piece of computation could say, okay, let's create a new thread to do that. Unfortunately, in practice, again, that's conceptually possible, but it's in practice too expensive. The process of creating threads and destroying threads costs something, needs the operating system to get involved doing that and managing all these threads. So in practice, that's generally not a good idea. Especially if we have very large if our application consists of very large numbers of small tasks, small as in small amount of execution time. So instead, the concept we can think of is that tasks are executed by some pre-existing pool of threads. So what we do is we create a fixed number of threads, and in practice, we probably want to match that number of threads to the hardware resources we have available. Okay? So as I said before, we typically think about this one-to-one mapping of threads to cores for performance reasons. So what most parallel programs, so particular OpenMP programs, do is that they create a number of threads when they start executing, which is essentially matched or designed to be matched to the available hardware resources. And those threads are kept alive for the entire duration of the program. But then we can think of decoupling the notion of tasks and threads by having this fixed number of threads, and then tasks we're able to submit tasks to this pool of threads. Some thread in the pool will execute the task. Maybe we have some control over which it is. Maybe we don't. Okay, maybe it's just entirely up to the runtime system to decide. And then at some point in the future, we have some guarantee about when the task is completed. And add a little bit of more complexity to this, a little bit more power. We also have the notion of tasks may not be ordered with respect to other tasks. Okay, so although we might identify things which are independent of each other, but we can also have dependencies between tasks. We can also impose requirements which says that this particular task must execute before this other task, but otherwise it's independent of other tasks. Okay. So with that idea in mind, let's talk a bit about parallel loops, because in reality, and in particular in the scientific codes, loops tend to be the main source of parallelism in most applications. So most of what we end up doing with OpenMP is parallelizing loops. Okay. So George asks, how do threads know which tasks have been executed already? Does that info have to be stored in shared memory? Okay, so this is the responsibility. This will typically be the responsibility of the runtime. Okay, so essentially, OpenMP and other APIs have basically have a library associated with them, and the functionality of that part of the functionality of that library is to manage all the parallelism. Okay, so it's to take care of creating threads, synchronizing threads, managing what threads execute what pieces of code when. And if we have tasks with dependencies, then it's the responsibility of the runtime to manage that. So that's a fair bit of complexity, which is it's hidden away from us as an OpenMP programmer, but underneath the runtime library is keeping track of which tasks have been executed. And yes, effectively, that will be stored in shared memory somewhere underneath. But managing that is quite complicated. Okay, so the runtime has to maintain lists of outstanding tasks and lists of dependencies, and the way it's usually implemented is that when a task is created, it will be created with a list of the tasks that it depends on. Okay, so it will and that task will not be allowed to run until all its predecessor tasks have been ticked off the list, if you like. Okay, so when its predecessors, when the tasks it depends on execute, then that will be noted for that task, and that task is not allowed to run until all its predecessors have been run. Yeah, so there's a fair bit of, in order to manage systems like that, there's a fair bit of complexity going on underneath. Okay, so loops. So the concept here is really straightforward. Okay, if the iterations of a loop are independent, in other words, they can be done in any order without affecting the result, then we can share out the iterations of the loop between different threads. Okay, so suppose I have a loop like this, which adds together the values in two arrays. Okay. So that's a nice example because it doesn't matter what order we do those additions in, the result will be the same. So here we've got 100 iterations, so we could consider, okay, and we have two threads, just do something very simple, do the first 50 iterations on one thread and the second 50 iterations on the other thread. I should emphasize here that I don't want to give you the wrong impression. So a loop this small actually cannot be efficiently parallelized. The overhead of doing the parallelization here is way too big compared with the execution time of a loop of length 100, where it's just adding some values together. Okay, in practice, this loop would probably need to be of the order of 10,000 before you're actually going to realize some benefits from parallelism. Okay, the principle's the same. Okay, we just have to we do have to take into account the essentially the size of the tasks. Okay, if our computational tasks that we identify are too small, execute in too short a time, then we may not be able to effectively parallelize them because of the overheads involved. Okay, but conceptually, it's very straightforward. Okay, so really, what we're doing here is we're thinking of an iteration of the loop, or maybe a set of iterations or a subset of iterations of the loop as a task. Okay. So we're saying that one of these loop iterations, each of the loop iterations are independent of each other, so that we can different threads can execute them at the same time and still get the correct result. So Marty asks, will variables A0 to A49 be private variables? No, they won't. Okay, and these A and B will both be shared variables in this instance. Okay. But it's safe because different threads are writing to different elements of A. Okay, so there's no possibility of there will be no possibility of any race conditions here. Okay, so the concept implies of race conditions really applies at the word level, not at the not at the array or object level. Okay, so we're thinking about reads and writes to individual program words as being the problem with race conditions, not concurrent access to higher level data structures. Okay, so the last thing I wanted to talk about in this section is reductions. Okay, so reduction is one of these operations which produces a single value from associative operations like addition, multiplication, maxes, mins, logical and, logical or. Okay. So in practice, additions, maximums, and minimums are the common ones we come across. So think about a piece of code like this, where we are essentially adding up, we want to add up the values in an array, okay, and store the result in a scalar variable b, okay. So we start off, we set b to 0, and then we just loop over the array and add the values into B. Okay. So the question is, how can we effectively exploit parallelism in a case like this? Well, if we just do the simple thing of dividing the loop iterations between threads, then we have the problem that we talked about before. Okay, we would have B as a shared variable, which it would have to be in this case for all threads to be able to add to it. Then we'd have a race condition because we've got different threads trying to update B at the same time. So some of our updates might get lost. Okay, we have a race condition. We'll get non-deterministic results. If we synchronize our threads in such a way as to allow only one thread at a time to update B, then we'll get the correct answer, but we'll have removed all the parallelism. And in fact, we'll have done even worse than removing all the parallelism. We'll have added some synchronization overheads as well. So the resulting program is likely to be slower than just running it on a single thread. Okay. So that doesn't help us either. So what can we do instead? Okay, well, the answer is fairly straightforward, really. What we can do is get each thread to accumulate its own private copy. Okay, each thread to execute a subset of iterations and accumulate a partial sum of B in its own private variable, and then add those copies together at the end to give the result. Okay. So provided the number of operations, so provided the value of n here is much bigger than the number of threads, then almost all those operations which are accumulating into private copies can proceed in parallel, and then we need a few synchronized operations, okay, so order of the number of threads to combine the partial results at the end. Okay. So in practice, it is possible to get, to extract all the available parallelism, lots of parallelism from patterns like this. And as we'll see later on, so OpenMP has some really nice support for doing this automatically for you. Okay, so OpenMP makes exploiting parallelism in this kind of pattern really very straightforward. Okay, so in that case, I suggest we give ourselves a break, and I'll resume again at 11:15. Okay, before we go, Anthony has a question. Okay, is there a thread which is responsible for the final add? The answer is maybe. Okay, the details of how that's done is down to the implementation, and there are different ways of doing it. You could get one thread to do the final additions. That's one possibility. Each thread might do its own addition, but do it in a synchronized way. In practice, what's actually done is some sort of tree-based algorithm. Okay, so the most efficient way of doing it is to use a tree where you combine the results in a well, it might be a binary tree, might not be. Okay, it might be a bigger fan in than two. So yeah, that's as far as OpenMP is concerned, that's down to that's an implementation detail. But there are multiple different ways which you can handle that. Okay, so welcome back, everybody. So this session, I'm going to talk about some of the fundamental concepts in OpenMP without really getting into too much details of the syntax yet. That'll come tomorrow. Okay, so what I'm going to cover in this session is some of the basic concepts underlying OpenMP. I'll talk very briefly about the history of OpenMP, of where it came from and its current status, and some practical stuff about how you compile and run OpenMP programs. Okay, so what is this OpenMP thing anyway? So OpenMP is an API designed for programming shared memory parallel computers. It uses the concepts of threads and tasks that we talked about earlier. It's a set of extensions to Fortran, C, and C++. And these extensions consist of three things. The most important one is compiler directives. So I'll say a bit more about what those are in a minute. But there are also runtime library routines and environment variables that also form part of the API. So what's a directive? A directive is a special line of source code that has meaning only to certain compilers, or has meaning only if a compiler has a certain flag set. So it's an extension to the underlying base language. So a directive in OpenMP is distinguished by what's called a sentinel at the start of the line. So the sentinel is just the sequence of characters which says this is an OpenMP directive and not a statement in Fortran C or C++. So for OpenMP, the sentinels are for Fortran, $OMP, and for C and C++, #OMP. The reason it's done like this is that it means that the OpenMP is easy for the compiler. It makes it easy for the compiler to ignore OpenMP directives if the code is just compiled as regular sequential Fortran C or C++. So in Fortran, because the sentinel starts with an exclamation mark, without OpenMP enabled, that'll just be treated as a comment and ignored. And for C and C++, #OMP is a preprocessor directive, which will, again, without OpenMP flags being set, that'll again just be ignored by the compiler. So the reason for doing it like this is that it doesn't guarantee it, but it gives you some ability to write code which functions correctly both as plain old sequential code and as OpenMP parallel code in the same code base, and you can choose, depending on how you compile it, which version you're going to build. Okay, so it's a say you have to do a bit more work than that. You have to maybe, if there are runtime library routines in there, you have to do something to deal with those. It's also possible to write. You have to be a little bit careful in some circumstances. It's possible to write OpenMP code that doesn't function correctly as a sequential code just by ignoring the directives. But this gives you most of what you need in order to be able to do that, which is attractive from a software engineering point of view. It's nice to be able to have code that builds correctly, either with or without OpenMP. Okay, actually, so this would be a good point at which to ask you all, which is your preferred base languages. So if you could type in the chat box for me whether you're most comfortable with Fortran or C or C++ or some combination. Okay, so we're getting quite a good mixture here. Great, thank you. So got a good mixture of all three, actually, all three base languages here. I will, I've got examples in all, well, most of the examples here are in Fortran or C. As far as OpenMP is concerned, the differences between C and C++ are relatively minor. There are a few things which are sort of C++ specific, which I will mention as we go along. So I'll certainly mention both C and Fortran versions of everything, because those are the main different ones. Okay. So let's move on and look at parallel regions, because the parallel region is the fundamental parallel construct in OpenMP. And it's actually the only way in OpenMP that we get to create threads, as the only way that we get to actually execute anything in parallel. Everything else in OpenMP essentially built on top of this. It's actually turns out to be not particularly useful on its own, but it's important to understand how it works without anything else, so that you have a good understanding of really what's going on here. Okay, so a parallel region defines a section of our program. And the way OpenMP works is that the program always begins executing on a single thread, which in OpenMP terminology is called the master thread. So OpenMP program just behaves like a regular old sequential program, until we get to the first parallel region. And at that point, at least logically, the master thread then creates a team of threads. Okay, so this is what's called a fork join model of parallelism. If you've heard of that, great. If you haven't, then that's just a piece of terminology that's used for this style of parallelism, where we alternate between sequential and parallel parts. So the master thread creates a team of threads when the parallel region is encountered. Then every thread executes the block of statements which is inside the parallel region. And at the end of the parallel region, there's a synchronization point. Because what happens is that the master thread waits for all the other threads to finish that block of code, and then it carries on continuing executing the next statements on its own. Okay, so it's a little bit easier to think about with a diagram, and okay, sneak preview of some syntax here. Okay, so in Fortran, parallel region is a block of code between a parallel and end parallel directives. In C and C++, it's the block of code, usually in curly braces, which follows a hash pragma OMP parallel directive. So what happens these cases are equivalent. So what happens is we start off executing only on a single thread. So when the program starts executing, just running as though it was a sequential program. When we get to this first parallel region, what happens is the master thread then creates a team of threads. So in this instance, I've shown a total of 8 threads. Okay, and the master thread always takes part. So the parallel region is executed by the master thread and 7 other threads in this case. So the master thread always participates in the parallel region. It always becomes thread number 0. Okay, so threads have numbers. We'll see that how that works tomorrow. But the master thread always becomes thread 0 inside the parallel region. So what happens is then all 8 threads execute this block of code inside the parallel region. And then at the end parallel, or the end of the parallel block in C++, the master thread waits at this point until all the other threads arrive at this point in the code. Okay, so there's an implicit synchronization point here. Once that happens, once all the threads have got there, then we're now outside the parallel region. We're back in what OpenMP terms the sequential part of the program, and we're back to single-threaded execution on the master thread. And then we can repeat this process as many times as we like throughout the lifetime of a program. So a long-running application might, could execute millions of parallel regions during its lifetime. So obviously, if we're looking for efficient parallel programs, then we want most of the execution time to be spent in the parallel parts and not in the sequential parts. And also, we don't want these parallel regions to be too short, because there is some overhead with starting up and shutting down and synchronizing the threads at the end of the parallel region. It's not massive. It's of the order of a few microseconds or tens of microseconds, depending on how many threads we have and the hardware involved. Okay, but it's kind of that level. So if a parallel region is, parallel regions execute for if the amount of code in here takes less than a microsecond, for example, then this won't, we won't be onto a winner here for performance reasons. Okay, the overheads of starting and stopping the parallel regions will tend to dominate. Okay. So that's essentially the fundamental idea here. In practice, the threads, the underlying operating system threads that are going to execute here are not created and destroyed every time. Okay, because again, that would be too expensive. What actually happens is down to the implementation. So it's not actually defined by OpenMP, but what most implementations do is they will actually create the threads at program startup and keep them alive for the entire duration of the program. And as long as every parallel region uses the same number of threads, then those threads will just get reused over and over again. And they will still exist in the background doing nothing, or, well, not quite necessarily doing nothing, okay? Potentially consuming CPU cycles during the sequential part here, okay? We don't really know what's going to happen. We can give some hints to the OpenMP runtime about what we'd like to happen, but most of that is down to the implementation. So logically, we're creating and destroying threads, OpenMP threads, if you like, for every parallel region. In practice, the implementation underneath is not actually creating operating system threads every time. It will create them once and keep them alive. And then it'll have to react, for example, if this second parallel region, if we asked for 12 threads instead of 8, then the runtime would then have to go away and create an extra 4 operating system threads at that point. But say in a HPC context, so when we have dedicated compute nodes and so on, then that situation doesn't really occur. We're almost always going to fix the number of threads at the beginning of the program execution and use that number of threads for every parallel region. So no, OpenMP is much more flexible than that, but that's very much the typical use case. Okay, any questions about that? Okay, let's move on then. Talk about shared and private data. Okay, so already talked about the idea. So how does that manifest itself in OpenMP? Well, because we've got this parallel region structure, when we're inside a parallel region, variables can either be shared or private. And those behave how you'd expect, okay? So all threads see the same copy of shared variables, and all threads can read or write shared variables. And each thread has its own copy of private variables, which are invisible to other threads. So a private variable can only be read or written by its owning thread. Well, that's true up to a point, okay? In practice, it may be possible to access another thread's private data, okay? And there isn't really anything stopping you doing that. So, for example, so one thread could take a pointer to a private data object, store that in a shared variable. Another thread can read that pointer and then try to dereference it and access the associated storage. And there isn't really there's no protection against that typically. Okay, it's not going to cause an error. You won't get a segmentation fault from trying to do that. But okay, first of all, the behavior is unspecified. So the OpenMP specification makes no guarantees as to what happens if you try to do that. It might or might not work. And perhaps more importantly, it's terrible coding style. Okay, it's just the most awful thing you can imagine doing is trying to, is subverting this distinction between shared and private variables is like this. So it would just be the most awful way to write code and confuse yourself and anybody else who's reading it. Okay, so basically you can't do this. Okay, even if you think, well, actually you can. Okay, in practice, it's not something you would or should ever do. Okay, so parallel loops. So in it might have occurred to you, well, actually, this parallel region thing isn't actually terribly helpful because, if all the threads are executing the same code, then how do I actually do anything useful? Well, and that's a good point. One thing you can do is, as I said before, every thread has its own number, has its own thread ID. So inside a parallel region, threads can choose to do different things based on their ID. But that style of coding is actually relatively rare. Okay, and that's because mostly what we want to do is parallelize loops. And so, although in a parallel region all threads execute the same code, OpenMP also has directives which indicate that work should be divided up between threads rather than replicated. And the term that OpenMP uses for this is called work sharing. And because loops are the main source of parallelism in many applications, as talked about before, OpenMP has a lot of support for parallelizing loops. And so there are, as we'll see tomorrow, there's a number of options which allow us to control which loop iterations are executed by which threads, and other features that help us deal with parallel loops a lot. So doing reductions automatically for you, collapsing multiple loops in a loop nest into a single parallel loop, all that kind of stuff is supported by OpenMP. So you very rarely have to resort to programming with bare parallel regions and using thread IDs. However, it's important to stress that OpenMP does not do any automatic parallelization, okay? And it doesn't do any checking. So it really is up to us as programmers to ensure that the iterations of a parallel loop really are independent of each other and that there aren't going to be any race conditions. So, I mean, there are, some compilers do have capabilities, or some usually fairly modest capabilities, but some capability of automatically parallelizing loops. There are other tools which can do this for you, but OpenMP does not rely on any of that technology. Okay, so OpenMP will not automatically parallelize loops for you, nor will it check whether your loops contain any race conditions or dependencies between iterations for you. It's up to us to make those guarantees. So we'll talk about a little bit towards the end of the course. Okay, There are some tools which will help you detect, or which are capable of detecting bugs like race conditions, but they're not. They're different from traditional debuggers, and the reason that it has to be done by separate tools is effectively that the problem it's fundamentally intractable to detect race conditions statically in code. Okay, it's basically not possible to do it. Okay, in other than very simple cases, but in the general case, it's impossible for the compiler to do compile time checks for race conditions. Okay. So yeah, parallel loops like this are very common. There's kind of restriction on what you can do here. So the straightforward OpenMP mechanism for parallelizing loops only applies to loops where the iteration count, so how many loop iterations they're going to be, can be computed before the execution of the loop begins. Okay, and so it doesn't have to be compile time known, but the runtime has to be able to calculate how many iterations there are going to be before the loop executes. So you can't use this mechanism to treat things like general while loops. There are other ways of handling that, which I will not be covering in this course. Okay, that's an advanced topic which is covered in when we run the advanced OpenMP course. Okay, so we talked about the importance of synchronization earlier on to avoid race conditions. So the main ones that are available to us in OpenMP are these ones. So the principal one that we use all the time is a barrier. So a barrier is a full synchronization point between all the threads in a parallel region. So when we reach a barrier, it's a point where all threads must arrive at the barrier before any thread can proceed past it. Okay, so typically places where this happen are at the end of the parallel region, which you've already seen. So where the master thread is waiting for all the other threads to arrive, that's a barrier type synchronization. But also at the end of parallel loops, by default, there's an implicit barrier synchronization as well. How does this help? Well, it means that we can, it helps us to ensure there aren't any race conditions, because when we have a barrier, we know that all previous reads and writes by all the threads have completed, and that no subsequent reads and writes by any of the threads has happened. Okay, so we're really dividing all the accesses into a very clear before the barrier and after the barrier. So that's a straightforward mechanism for ensuring that we don't have any race conditions. And it's effectively the one that OpenMP uses all the time, and it's implicitly there in some of the commonly used constructs. This has its strengths and weaknesses. So OpenMP is designed to be relatively easy to use. So it tries to support you as a programmer in not having race conditions. But it means the downside is that you can end up with your code containing a lot of barriers. And barriers are relatively expensive synchronization operations. So I mentioned before that the overhead of a parallel region is on the order of a few microseconds typically. Actually, most of that overhead comes from the barrier synchronization. Okay, so that's the cost of the barrier synchronization accounts for most of that. So it's also on the order of a few microseconds typically. So if we encounter barriers lots and lots very, very frequently in the code, it's very easy for that overhead to build up and just completely dominate the execution time. So although it's convenient, it allows a relatively safe programming model, it is possible to run into excessive overheads because OpenMP is inserting a lot of barriers for you effectively. So that's again something we'll talk about in the we'll revisit when we talk about performance, but it's something that's always worth bearing in mind. Second main mechanism we have is what's called critical regions. So this is a section of code which only one thread at a time can enter. So this is exactly what we need if we want to protect modification of shared variables, updates to shared variables from race conditions. So we can place those updates inside a critical region, and that makes sure that only one thread at a time can execute that. It doesn't make any guarantees about the ordering. Okay, it doesn't say which thread's going to execute the update in any before any other thread, and so it doesn't have any ordering guarantees associated with it. It just makes sure that only one thread at a time can execute that piece of code. And then the third one is kind of a special case of that, which is atomic accesses. So these are basically a single access, an update, a read or a write of a variable, which can be performed by only one thread at a time. But as we'll see, we'll talk about the later on synchronization topic, the distinction between critical regions and atomics. So the one-liner here is that atomics are a special case. They only apply in certain situations, but where they do apply, they can be much more efficient than critical regions. So I'll leave it at that for now until we revisit it in later lectures. Okay, does anybody have any questions before we move on to our brief history lesson? Okay, so Daniel asks, when we fix the number of threads at the start of the program, does that also introduce any overhead or potentially impact performance? So there is always going to be some, the threads need to be created sometime, okay? So the cost of the operating system actually creating the threads has to happen at least once somewhere. And so having it happen at the very start of the program is kind of as good a place as any, really. And the overhead is typically fairly small. Okay, if we're going to do it once, it's going to be on the order of a millisecond, something like that, probably. So for most practical purposes, it really isn't a problem. And the advantage of creating all the threads at the beginning and then reusing them for every parallel region is that the cost of starting up the parallel region then becomes very small. There is a question about what happens to those threads in between parallel regions. Okay, so the master thread is executing something. All the other threads are doing nothing in between parallel regions. Or they don't have any work to do. So what are they going to do? Well, that's down to the implementation. And in practice, what they will do is that when the parallel region ends, initially, typically the threads will actually busy wait. they will actively spin and consume CPU cycles in a while, basically in a while loop. And the reason for doing that is that's the situation that makes it almost zero overhead to reactivate them into the next parallel region. It's also potentially unpleasant. I mean, again, it depends on the situation. In a HPC context, that's probably fine, okay, because we can't, there's nothing else that we can do with those, usefully do with those cores anyway, most likely. In other situations, you might want, you think about having, where you've got more than multiple processes running on the same system. It's you've got a shared system in some way. Then it might be nice to other users of the system to actually free up those hardware resources in between parallel regions. So what most implementations will do is that they will spin the threads for a while, up until some certain time limit, and then the threads will be put to sleep so that they're no longer consuming CPU cycles. So that means the next parallel region has to wake them up. That's less expensive than recreating them from scratch, but it's more expensive than just tripping them out of a busy wait loop. So it's kind of a compromise. And there are ways you kind of don't really know what the implementation's doing. There are methods, there are hints that you can in OpenMP where you can hint at which behavior you'd prefer as to whether you want your threads kept busy waiting, which is usually what we want in an HPC context, or whether you want the operating system to put your threads to sleep in between parallel regions, which might be beneficial in other contexts where you have shared systems with other things going on, and you want to be able to free up resources. One difficult situation that you can get into with some applications is it's possible to write applications that use more than one threading library. Okay, so you might use you can end up with basically where you write an application that in some parts of the code is parallelized with OpenMP. Other parts of the code for example, might call library routines which are internally threaded somehow. And those internal threads might not be managed by OpenMP. They might be POSIX threads or something else, okay, by being managed by a different runtime than OpenMP. And in that case, it is important that the OpenMP threads are not consuming CPU cycles in between the parallel regions, because that's where you might want to make your cores available to run the other threads that are active inside some library, for example. But for the most part, so the common use case is start the number of threads at the beginning of the program, keep them alive, keep them spinning between parallel regions so that the overhead of the parallel region is kept as small as possible. Okay, any other questions? Okay, so our history lesson. Well, OpenMP is now quite old. So especially for people who are younger than me. So I remember the beginning of it. It was well inside my professional career, but it won't have been for many of you. So it'll be the foundation of the OpenMP ARB will be celebrating its 30th birthday in a couple of years' time. So what was the problem it was trying to solve? Well, way back when, okay, so here we're talking about the sort of early to mid 1990s. There was a historical lack of standard. This style of programming did exist, okay. This way of doing parallelism with directives and shared memory did previously exist. But what happened was that every hardware vendor provided provided their own compilers which implemented a different API for doing this kind of thing. It was mainly directive based at that time. It was almost all for Fortran, and that just made it hard to write portable code. Okay, you needed a different set of directives for every machine that you wanted to run your code on. So the idea of OpenMP was to say, okay, let's have a universal standard for this style of parallelism. Okay, so that's what happened. So a bunch of commercial companies got together and set up the OpenMP ARB. It now has I think more than 30 members, various different organizations, both from the commercial side, the hardware manufacturers and people who write compilers, and from sort of the academic side, and also from sort of government labs as well. So there's now a large collection of, reasonably large collection of organizations that make up the OpenMP Architecture Review Board. So we started off with Fortran, okay, and then C++ came a little bit later, and at that time they were separate specifications, which turned out to be messy and complicated because things were duplicated or contradicted each other. So in 2005, so version 2.5, they got combined into a single document which supports all three base languages. And then there have been a bunch of revisions since then. So most important one, so version 3 added a whole lot of extra features, including tasks, which we're not going to talk about in this course, but other things like better support for loop parallelism, nested parallelism, which we will discuss a bit. And then kind of the big major change came in with 4.0, which was the ability to offload code to accelerator devices like GPUs. So again, I'm not going to, that's a separate course. I'm not going to talk about that here. We are in the process of developing a new course specifically about programming GPUs with OpenMP. So we should be running that towards the end of this year. So if you're interested in programming, in GPU programming with OpenMP, then keep your eyes out for a new course coming soon. Okay, and then again, there've been various revisions since then. We've reached a situation which often happens with standards where the support from different compilers is a bit variable. So at the moment, we're in the situation where most current implementations comply with either 4.5 or 5 point something, except for this for the offloading to GPU, and that has less widespread support. Okay, so you'll find that in some compilers and not others, and where you do find it, it's available for some types of GPUs and not others, depending on who makes the GPUs and who's producing the compilers and so on. So for the offloading stuff, this support, you really have to kind of look carefully and say, okay, what hardware am I running on? So which features do I need? That would determine which compilers will support them. On the CPU side, it's really not so bad. Okay, so pretty much as long as you don't want anything beyond 4.5, every implementation will support that. So there's a few things in 5 and later which you might need if you want to use those features. You might need to look at the compiler documentation to see whether they are and how well they are supported. Okay. OpenMP has its own website, www.openmp.org, and the main interest for that really is the language specification documents. Well, maybe, okay. Those documents have now reached the stage where they are very big, very difficult to read, okay, like most language specification documents. And they are perhaps of limited use compared to what they were in the early days, where they were actually quite short and readable. The other thing that is there is a document which contains a lot of examples. Okay, so I mean, it's not quite every single feature has an example to go with it, but it's quite close. So pretty much any feature you're interested in OpenMP, there's a document which contains example code fragments, which shows you the typical way of using them. So these days, the example documents are actually probably more helpful than the actual specification documents. So those are perhaps that would be, you know, if you're unsure about something, you want to find out more about it, then that's possibly the first place to look is in the examples rather than in the actual specifications themselves. Okay, there's various other bits and pieces on the website. So there's more or less a list of all of compilers that support OpenMP and what versions they support and so on, which is kept reasonably up to date. If you like textbooks, I'm afraid the situation is not that great. Okay, these pair of books are probably the best option. But they only really go up to, they don't cover anything beyond version 3.0. So most of what you use in practice probably will be older features before version 3.0, but there isn't much else in there. Oh, actually, okay, just maybe 4.0. Okay, is for the second book. Okay, practical stuff. So compiling and running OpenMP programs. So OpenMP these days is built into most of the compilers you're ever likely to come across in this sort of, you know, scientific computing HPC space. It's less true if you're working with, you know, embedded processors or, you know, mobile phone processors or things like that, you know, smaller chips, you know, smaller lower power chips. But, you know, for high-end server chips, most of the compilers you're ever likely to come across do have OpenMP support. So in order to compile an OpenMP program, you need to add a flag which is compiler specific to your compile and link commands. So you have to look at the documentation to figure out what it is. So it's for GNU compilers, GCC, G-Fortran, for Clang, for Craze, C++ compilers, which are actually Clang based. It's -F OpenMP. For Cray Fortran, it's -H OpenMP. For Flang, it's -MP. For Intel compilers, it's -Q OpenMP. So yeah, you just have to figure out what the right flag is to add to your compile and link commands to enable OpenMP. And then, okay, sneak preview of another bit of the APIs in one of the environment variables. So the number of threads which will be used by default for parallel regions is determined at runtime by the value of an environment variable called OMP underscore num underscore threads. So the absolute typical use case is to set the value of this environment variable before you run the program. So either on the command line or in your batch script if you're running batch, if you're submitting to a batch system. So you'd export the value of OMP num threads. Okay, so say you want 4 threads for every parallel region. Okay, and then that's picked up at runtime and used. So the number of threads does not need to be compile time determined, and it's generally, I would consider it good practice not to encode the number of threads at runtime. In fact, I would fairly strongly encourage you to write code which does not write OpenMP code, which does not know anything about the number of threads that are going to be used. And then you just run it in the same way as you would run a sequential program. You just type the name of the executable. OpenMP doesn't require anything in the way of a launcher application like MPI does. So there's no equivalent of MPI run or MPI exec or whatever it is or srun or whatever it is you use to launch MPI programs. You don't need that for OpenMP. It's fine to you can srun an OpenMP program on ARCHER2. Okay, so if you're using Slurm, then you can launch it. You can launch OpenMP with srun. It helps to have control. It helps you to do that is useful because it you can use Slurm's controls over hardware resource allocation. So which cores you're going to, which cores you want to run on, and so on. But it's not necessary. Okay, any questions? Okay, so just to introduce the very first practical exercise, it's just a simple, just to get you started to be able to compile a run a trivial Hello World program. So it's all you can do so far. I haven't taught you any syntax yet. So, but of course, feel free to read ahead in the lecture notes if you want to before tomorrow. So if you want to just try that, and make sure you can get hold of the template codes, build the Hello World, run it. If you want to do that in the remaining 20 minutes or so that we've got, then great. I'll be around if you help out if you've got any problems. On the other hand, if you want to head off now, that's absolutely fine. Do it in your own time. And if you've got any problems, then post in the on the course chat linked from the course web page. Okay, so what can you do? What can you do with Hello World? Well, you can say, okay, you can set the number of threads with the environment variable, and make sure you can do that. And that's just one thing to think about. Okay, so if you run the code several times, do you always get the same output? And if not, why not? Okay. Great. Does anybody have any questions for today? Okay, great. So as I said, I'll hang around here until past, until if anybody needs any support with getting getting their code up and running on ARCHER2, or otherwise. Thank you very much, and I'll hopefully speak to you again tomorrow.